Okay, well, welcome everyone to a new semester for TCS Plus. So for those of you who don't know, TCS Plus is a fully online seminar. We've been going for over 12 years now, and we have a wonderful collection of talks that are all recorded and are being set up. So the first talk for this semester is we're very excited to have Janani Sundaresan. Janani is a PhD student at the University of Waterloo who's done really a lot of fantastic work on streaming lower bounds and communication complexity. And today she's going to tell us about distributed triangle detection. Um, a few things before we begin. I do want to encourage everyone to keep their cameras on. I mean, this is an online seminar, but it's always a lot more pleasant for Janani and for everyone else if there's a little bit of visual feedback. The talk is being recorded, so I'll upload it on YouTube. But if you have a few questions or a few things that you want to discuss that you'd like to not be recorded, well, usually after the talk, the room remains open and we can just hang out and ask for further questions. With that being said, I also want to thank the rest of the organizers. This includes Clement Kanan, Rachel Cummings, Sumega Garg, Shivam Nadampali, and Yasmin Nasari. But with that said, let me hand over the floor to Janani and please take it away.
Okay, thank you for the nice introduction. And also, thank you for inviting me to speak here. And I want to thank all the organizers also. Uh, TCS Plus has been a great resource for me to watch. Some of the talks are always fun to watch. So, yes, okay. And in the middle of the talk, if anyone has any questions, you can always stop me and ask me questions or put something on the chat. Anything works. So let's get started. I'm going to talk about distributed triangle detection. This is joint work with my advisor, Seber Asadi, and we're both from the University of Waterloo. Uh, let's dive right into the model. We're looking at this model called the local model, and this is one of the standard models considered when you want to process graph in a distributed manner. And this was introduced by Lineal in 92. You have a graph G with n vertices. All of these vertices are going to have unique identities from 1 to n. You can think of each vertex as a player or an agent that has some specific input and they want to process this input. Okay. So in this example, we have 8 vertices and each vertex has one unique identity from 1 to 8. So let's see what these vertices actually know. So vertex 2, this agent is only going to know its immediate neighbors. By that, we mean that it's going to be given a list of identities which all belong to its neighbors. So 2 is going to see that it has edges to 4, 6, and 7, and it doesn't know anything else about the graph. So this vertex 1, for instance, is going to know that it has an edge to vertex 8, but it won't know anything else about the topology of the graph. So this is going to be what the information that each vertex has looks like. They will just have a list of their own neighbors, and that's it. So in addition, they are going to also be given just a source of random bits that only they can see, that is private to them. So they have their list of neighbors and they have this random source, and then they can do whatever they want with it. Um, what they are actually allowed to do to talk to each other is to use the edges inside this graph as communication channels. We're not going to put any restriction on what these messages are or the length of the messages. So vertex 7 is going to look at its neighborhood and send any message it wants to vertex 3, and it can send a different message to vertex 2, and so on. So it can also use its private randomness to figure out what this message is. So in one round, each vertex is going to be able to send arbitrary messages of any length across each of its edges. I want to reiterate here, we're not saying that they should send the same message. They can send different messages across each edge. A protocol to process this graph can take many rounds. So in one round, you send a bunch of messages and you also receive a bunch of messages. You can look at these messages and then figure out a new message for the next round and so on. And when we want to process this graph, the output is also something we're going to ask for in a distributed manner. So we'll see what this means for the specific problem later. And the main aim here is to just minimize the total number of rounds. And that's it. So we want to process this graph while not using too many rounds. So the specific problem we're going to be looking at is triangle detection. If the underlying graph has a triangle, we want at least one player to say yes. And if there's no triangle, we want all the players to say no. So this is a very simple problem. And so what can you actually do in one round in the model we defined for triangle detection problem? Okay, so let's do something very simple. Vertex 2 is just going to try and send a list of its neighbors through the edges that it has. So the message from vertex 2 to 7 is going to say, I have two other neighbors, 4 and 6. So I'll just send this message to vertex 7. If I'm sending a message from 2 to 6, I will just let this 6 vertex know that I have edges to 4 and 7. And if I'm sending a message from 2 to 4, I'll just tell the vertex 4 that I have an edge to 6 and 7 and so on. Okay. So vertex 2 is just trying to communicate its neighborhood to its neighbors. And if all the vertices do the same thing in the first round, then they're going to know the entire two-hop neighborhood in the graph, like the two-hop neighborhood surrounding them. Because now let's look at the 6 vertex, for instance. It knows that it has edges to 5 and 4, but it also knows the edges that 4 and 5 themselves have, and the same thing is true for vertex 2 also. So vertex 6 will know its entire two-hop neighborhood. But we said we're trying to solve triangle detection, which means if you know the two-hop neighborhood, you're actually solving this problem completely. It is simple enough. There is nothing hard about this. You can solve this in one round. Um, okay. So the immediate question to ask is if the communication over these edges actually has some constraint. So instead of allowing these vertices to say whatever they want with arbitrary message length over these edges, we're going to ask them to communicate only order log n length messages over each of these edges. So this upper bound on the message length is going to be called bandwidth. And we're fixing this bandwidth to be order log n. This is the other standard model looked at in distributed computing called the CONGEST model. And this model was defined by Peleg in 2000. So here, whatever we talked about in the local model is exactly the same with regards to what the vertices know and have. The only constraint is the bandwidth over the edges is limited to order log n, and they cannot send long messages of arbitrary length. If you look at this triangle detection problem now in this CONGEST model, it is not going to be easy anymore. It's not clear what you can do. More generally, this problem is very well suited to study bandwidth constraints, which is upper bound on the length of messages, as opposed to locality, or how much around you do you need to know, because if you just know your two-hop neighborhood, this is going to be super easy. But the bandwidth constraints are the ones which cause this problem to be hard. So any questions till now about the problem, the model, anything? Okay. So let's see what you can do in the CONGEST model we defined with this upper bound of order log n on the length of the messages. So you can still try to send your neighborhood to your neighbors, but you're just going to use many rounds to do it. So in one round, let's say this vertex 4 is trying to communicate its neighborhood to vertex 6. I'll only be able to send one edge. And in the next round, I can send the other edge I have to 5. So more generally, sending your entire neighborhood is going to take order n rounds because you're only going to send one edge in each round. So the trivial algorithm we had to solve triangle detection by just sending your neighborhood is now going to take order n rounds. So the question is, can you do better than order n rounds? And it turns out you can do better. So in this congest model, Izumi and Legal gave the first little o of n round algorithm for this problem, and they were able to do it in O tilde of n to the two-third number of rounds. So this bound was improved by Chang et al., and they gave an algorithm which uses O tilde of n to the one-third number of rounds. So both of these algorithms were randomized. So when it comes to deterministic algorithms, Senza-Hillel et al. Was able to give an algorithm that uses n to the one-third plus little o of one number of rounds. And Chang et al. Gave an algorithm then which again uses O tilde of n to the one-third number of rounds. So we're able to match the performance of randomized algorithms, and n to the one-thirds remains a state of art for both randomized and deterministic algorithms. Okay, so while we're talking about prior work and all these known results about these kind of triangle detection problems, I want to mention this survey by Karen Senza Hillel. This is a very comprehensive survey which talks about a lot of other subgraph and all the results. So this was very useful for us while we were looking at this problem. And so just all the details about the everything I stated in the earlier slide can be found in this survey. So let's continue and look at more prior work. You can also find this in the survey. So Abood et al. Was able to give a lower bound for this problem for deterministic algorithm, which says that you can't do it in one round. And that's it. And after this, Fisher et al. Was able to improve this lower bound to saying that you're not going to be able to do it in one round for randomized algorithms also. And as far as lower bounds go in the model we are looking at, this is all we know. We don't know any other lower bounds. People have looked at other models of computation which are algorithmically weaker to try and prove stronger lower bounds, and we can do something here. So if you look at this weaker model where the bandwidth is only one bit over each edge. So for the congest model, we said the bandwidth was going to be order log n, but now we're reducing this even further and saying the bandwidth is going to be only one bit over each edge. So in this model, Abud et al. And later Fisher et al. Was able to give a lower bound of omega of log n rounds for deterministic algorithms. And in another weaker model where if a vertex has to send the same message to all of its neighbors, then you can prove a much stronger lower bound of n to the 1 minus little o of 1. And this is also for deterministic algorithms only. And this was given by Drucker et al. So even in these weaker models, we are not able to prove anything beyond this one round lower bound for randomized algorithms. So the obvious open question, can you get stronger lower bounds for this triangle detection problem in this model, even for randomized algorithms with the standard bandwidth assumption of order log n bits per round in each edge? So this is what we're going to address. There are some reasons why we haven't been able to prove very strong lower bounds. So Eden et al. Showed that if you were able to prove an n to the alpha lower bound for any constant alpha, then you're going to prove strong circuit lower bounds, which are beyond the reach of current techniques. I'm not going to go into more details about what these are. We'll come back to this much later. But it's just that if you prove an established n to the omega of 1 lower bound for this problem in the congest model, then you're also going to prove very strong circuit size lower bounds, which we haven't been able to prove for decades. So this seems a little out of reach. But, well, if you can't get that strong lower bounds, then maybe you can get something weaker. So can you get n to the little o of 1 lower bound instead for this problem? Because the only thing we could do was say that one round is not enough. And this is precisely what we're doing. Our main result is the round complexity for triangle detection in this congest model is going to be omega of log n. And this is true for randomized algorithms also. And this is the first multi-round lower bound for this problem in this model. Prior to this, all we knew was that one round was not going to be enough. Any questions about the result?
Can you say a word about maybe how this n to the one-third upper bound works?
Yes. Okay. So they are in a very high level, they are going to split the graph into expanders. So the big breakthrough came because they figured out how to do expander decomposition in the CONGEST model. And once you go into the expander, after that, trying to detect triangles inside the expander is not going to be too hard because there'll be good routing algorithms. The main bottleneck is going to be from this specific routing algorithm for this expanded decomposition once you do it. And I will mention one more thing here. So the algorithms that I talked about are also going to be true for listing listing triangles, as in every triangle must be listed by at least one vertex in the graph. And this is like a lot of information to process. So n to the one thirds comes from this kind of barrier also. Like, for listing, we know we can't do any better. And we know strong lower bound saying n to the one thirds is tight for listing. So this current techniques of going into expanders and just trying to list all the triangles inside expanders is not going to give you anything better than one third. Thank you for the question. Any other questions, or do you have anything else you want to know about the algorithm?
No, I think that answers my question. Thanks.
So one question.
Okay.
So this lower bound which you show, it's an unconditional lower bound? Or
Yes, it is unconditional. Everything is information theoretic. There are no assumptions. No.
okay, okay. Thank you.
All right. Okay. If there are no other questions, we can proceed to the proof overview. So how do you actually prove lower bounds in this model? The main tool has been till now to go through communication complexity. Um, in a very high level, what is going to happen here? You'll have two players, Alice and Bob. You're going to split the set of vertices inside the graph, give some of these vertices to Alice and give some of these vertices to Bob. Alice is going to know all the edges incident to her part of the graph, and Bob is going to know all the edges incident to his part. There's going to be very few edges which in the middle which are known to both of them. So once you split the graph, then they'll be able to talk to each other and answer questions about this. Um, this technique of going through communication complexity has actually been very successful. Let's look at graphs which are very close to triangles. I am going to look at four cliques and other small cycles. Okay. So if I want to detect constant sized cliques of size at least 4, we can prove a lower bound of omega of square root n rounds. And if I want to detect any odd constant size cycle, I can even prove an omega of n round lower bound. For even length cycles, I can prove a lower bound of omega of square root n. So these are all very strong lower bounds that we have been able to prove. And turns out they're actually tight for some graphs also. Specifically for four cliques, this lower bound is tight. And for four cycles, also this is tight. The same thing is true for odd constant cycles. So we can prove actual tight lower bounds with this technique. So it has been very useful. But why are we failing? Let's go back to this picture of splitting the graph into two people. However, I split this triangle, at least one of these two people are going to have two nodes, which means now Bob has two nodes. Bob is just going to be able to look at all its edges and know whether this triangle exists without talking to Alice at all. So this is not hard if I just look at it as splitting between two people. They don't even need to communicate to each other. They can just look at their part of the graph and see if the triangle exists or not. Okay. So that's why this way of proving lower bounds is not going to work. But there are a lot of things you can use from communication complexity. And the main thing we're going to be using today is something called round elimination. So this was formalized and given as clean statement by Miltison, Nissan, Safra, and Victorson in 95. And after that, it has been proven to be very useful in a lot of structural load bounds and streaming load bounds. And round elimination with a different flavor has been used to prove low bounds in the local model also, although the details are a little bit different. So this is what we are going to be using today. Let's actually go into details of round elimination after this. But before this, any questions about why triangles are different? Are the graphs anything else? All right, okay. So more specifically, we'll go into what happens in round elimination and what you would need to prove a lower bound using this tool. The first step is going to be to construct a family of hard distributions. These are going to be distributions over graphs that you think are going to be hard for specific protocols with, let's say, R rounds, R minus one rounds, and so on. So you do this all the way till zero round, which just means that this is going to be hard without any communication. So once you did that, you're going to try and prove your result with a contradiction, which means you think that there should not be any good protocol for graphs sampled from DR. Okay, so let's assume that a good protocol exists that you think shouldn't exist. Now we're going to use this protocol, which solves graphs sampled from DR, and get a smaller round protocol which uses only R minus one rounds and solves graph sampled from DR minus one. So this is the big step that gives you what you want. We'll go into a little bit more detail about this later. If you can get these smaller round protocols, you keep doing this recursively till you end up with a zero round protocol. And this is going to do something non-trivial. Zero round as in it doesn't communicate at all. So without talking to anyone, these vertices are going to gain some information. And this will give you a contradiction because this will not be possible. So this is the framework for round elimination. Let's look at this specific step of how we're constructing these hard distributions. So the zero round hard distribution is super simple. By zero round, we just mean that there is no communication happening, and whatever graph we construct is going to be hard without any messages between these vertices. So there are going to be just three vertices, and each edge between these three pairs of vertices is going to occur independently with probability half. Okay. So if this happens, these vertices will not be able to guess whether a triangle exists with probability better than 7 over 8 without any communication. So this will be hard without them talking to each other at all. But if you give them even one round of communication, they can actually solve this very easily because they'll just be able to tell each other, this is my edge, and it's over. So in one round, whatever we had, this is super simple and easy to solve. But the one round hard distribution we construct is going to look like this. Okay. Um, what is going to happen here is this green vertex, for instance, will have a lot of neighbors. We're going to flood each of these green vertices with these orange vertices, which are going to be useless, and they do not contribute to whether a triangle exists inside this graph. But the green vertex is not going to know which of its neighbors is actually important. So when it looks at its list of neighbors, it won't know which ones it has to focus on to figure out whether the triangle exists. It'll just have like a big list. So we're swamping these things with other vertices which are useless. But this hard distribution is going to be very simple in two rounds. What can happen is these orange vertices we added, we force them to have degree only one. So they know that they're useless, which means in one round, they'll be able to tell the green vertices that we are not a part of a triangle. And in one round, you can actually get rid of all of them. So you will know that they're not important, which means these green vertices in the remaining one round, if they have two rounds, then they can solve this smaller three vertex instance very easily. Okay, so this one round hard distribution is going to be very easy if you have two rounds. But in two rounds, you can actually repeat the same thing. Take all of these vertices which were important in the one round distribution and just swarm them with a bunch of extra neighbors so they don't know which one is important, which one I should talk. So these pink vertices now are going to be a lot of vertices. The orange and green vertices will have a lot of neighbors. They won't know which one is important and what they should actually focus on. Okay, so let's repeat once more, like why is this distribution hard? So if I just have this first round, let me focus on this smaller one round instance. I will not be able to say anything useful about these instances to other vertices which are a part of this instance. So the orange one, for instance, will not be able to say whether it's orange or green because it won't know. And the same thing is going to happen for all these vertices from the one round instance. But these pink vertices which we added can be removed from the graph because they have degree only one and you can get rid of them. They will know that they're useless. So they will be gone after this first round. But now you're left with this one round instance and, well, only one round to solve it where you haven't really gained anything from the earlier round. And these orange vertices will still be a problem, but you can remove them from the first round because they can now figure out that they have only degree one and they're not actually a part of the triangle and they'll be gone. You're left with a zero round instance, but the first two rounds were mostly useless. You could not talk to your other green neighbors, which means you did not figure out whether the triangle is inside this graph or not. So this is why the distribution we construct is going to remain hard. And more generally for R rounds, this is what we're going to do. Take a smaller R minus one round instance, take each of the vertices of this instance and just flood it with a bunch of useless neighbors. All of them are going to have degree 1. If nr minus 1 is the number of vertices, then the total number of edges that each inner vertex is going to get is going to be some poly in nr minus 1. So this is going to be super large. And one thing I want to stress here, the IDs of your new neighbors which you've added, which are the pink vertices, and the IDs of your inner neighbors are going to be indistinguishable. So let's maybe zoom in a little bit to see what actually the input of some vertex from IR minus 1 looks like. So this vertex V, let's say it's from IR minus 1. It is going to have a big list of neighbors. K is going to be some polynomial in NR minus 1. And it won't know which one is a part of the smaller instance, which one is a part of the outer instance, and so on. So the main randomness which is coming inside the construction is going to be over the identities of these vertices. So the topology of the graph remains fairly the same, except for the underlying triangle in the zero round. The main randomness, the reason why randomness is going to matter is because these IDs are going to be indistinguishable. And so once you have this together with all of your neighbors, you're going to have IR as the larger instance. This is going to have NR vertices. NR is going to blow up by like a poly in NR minus 1 factor. So any questions about how we're constructing this hard instance? All right, okay. So this part of round elimination is over now. We've done this. This is the next part of round elimination. A good protocol for R rounds, we want to use it to construct a protocol for R minus 1 rounds. So more specifically, we have a protocol PyR. Let's just call it PyR. This solves R round hard instances sampled from DR. And we want to use it to solve R minus 1 round instances sampled from DR minus 1. And we'll just repeat this all the way till 0 rounds. So this, I'm going to visualize the smaller instance like this, and we have some protocol PyR. How can we actually use PyR to solve this IR minus 1 instance? So these are my only real vertices at this point. This is what I am focusing on. So the first obvious step, you want to be able to run this PyR on some instance. So you just want to construct a bigger instance so you can use what this protocol does. So this is going to be embedding the smaller instance inside a larger R round instance. This To do this embedding, just augmenting the model we're working with public randomness that all the vertices can see is going to be super useful. And this embedding is not going to be hard once we augment this model with public randomness. So whatever lower bound we prove with this augmented model is going to hold in the original congest model also, because we're only giving it extra power. Okay. So now all these vertices have one extra resource they can use, this big tape of public randomness that all of them can see. The first step is that your identities now should come from a larger set. Okay, so you go look at this public randomness and just sample new identities for yourself. But because this randomness resource is public, you can do this in a consistent manner that all of these vertices have different identities, basically. Okay, and you can do one other thing with it. So basically, you can take some specific subset and say these are going to be my fake neighbors. We'll see what fake neighbors are. So let's just look at this vertex 5. It has to have a lot of neighbors in the R round instance that it doesn't have at this point. So it's going to go to this list of IDs it knows, and going to go pick a new set of appropriate poly and NR minus 1 size and say these will be my neighbors inside the bigger instance. So the bigger instance doesn't actually exist. We're working with only these NR minus 1 vertices in the blue circle, but vertex 5 is imagining that these are my neighbors. So we want to try and run this protocol. So it's just the pink vertices are going to be fake from now on. They are just things which 5 says are going to be the IDs of my neighbors. And this is something that all the vertices can actually do in a consistent way because they have this global randomness. So all of these vertices are going to pick some subset and say, this is going to be my neighbors. And after this, we'll see what they can do. So yes. So they've actually constructed this big R round protocol. And all of these pink vertices are going to be fake imagined outer vertices together with this IR minus 1 that we had is going to give you this instance IR. So it's going to be as if this IR is exactly sampled from the hard distribution DR we had for R rounds. So what are we trying to do? Just to recap, we had an R minus 1 round instance. We had a protocol that solves instances from this distribution DR, and we want to use it to solve this. We've made some progress. We've constructed this new IR instance, which is exactly as if sampled from DR. And the one thing we did was give them this extra resource of public randomness. And now we can actually run PyR on this new instance. So one thing to note here, whatever imagined vertices we have, they all have degree only 1. So we're not creating any new triangles. Whatever property this IR minus 1 has in regards to whether a triangle exists is going to be true for the larger instance as well. But the main glaring issue here is if you're going to naively directly run this PyR protocol, you will need R rounds, and you do not have a budget for this. You only have a budget of R minus 1 rounds. So what can we do to get around this? This is why the technique is called round elimination. We want to eliminate the first round somehow. So more specifically, we'll figure out a way that all of these vertices inside IR minus 1, they are going to know what the first round message that they send and receive on this IR instance without actually talking to each other. So I'm not telling you yet how we can do this. It's just that we give a way where all of the vertices inside the blue part, which are the real vertices, they are going to know what are the messages that they would have sent in protocol PyR if they had gotten this bigger instance IR, and what are the messages they would have received from all of their neighbors in the bigger instance IR from in protocol PyR without actually talking to each other and using any communication. So if I want to be more specific, this protocol PyR inside this, there's going to be a distribution M1 of the first round messages. So this is going to be collectively all the first round messages sent and received by all the vertices. So we would want to sample messages with some resources they have. They have public randomness at this point, and they also have private randomness. We'll give them something else to do it. We'll come to that later. So we will give them a way to sample these messages, which is as close as possible to the distribution that M1 would have had in protocol PyR on this instance IR we constructed. So this is the main technical part, and this is where the bulk of our efforts went into. What we're doing is we're able to sample these first round messages from either public randomness or private randomness or some other sources so that the joint distribution of the first round messages and the input IR together is going to be close to the ideal distribution they would have had. The ideal distribution, as in the distribution that they would have gotten in PyR. So this is going to be very close to this distribution. Once we have these first round messages, after that, it's not going to be a problem. You can just continue running this protocol PyR you have just from the second round. Now you're only going to need R minus one rounds, so you'll be okay. You have enough budget to do this. And the rest of the round elimination proof is going to follow almost directly. You found a smaller round protocol and you keep doing this till you end up with a zero round protocol. So the one thing I haven't told you is how we actually sample messages. I will get into it next, but this is how the overview of the proof goes. So any questions till now?
Yeah, Janani, can you maybe say a few words about why you would not be able to exactly sample the messages from M?
Yes, okay. So we said, okay, I think it'll be clear once I actually get into the sampling process what the problem is. So I think we'll get to it in like 2.5, 3-ish minutes. Is that okay? And I can stop then, and then if you have any other questions, then I can answer then.
Okay, yeah, that's fine.
Yeah. Anything else? All right. Okay. So now I'm going to talk about how we can sample these first round messages. I am going to focus on this only for one specific vertex from this inner instance. Let's just say we're zooming into something, and I'm going to make, okay, yes, okay, now I know. Before we get into how we actually sample these messages, I just want to maybe, throw some things that vertex we can send inside a protocol so that we can keep this in mind. And the way we sample should be able to handle all of these possible protocols. So in short, we don't have any control over what protocol PyR does, and we should be able to handle any kind of messages that this sends. So Vertex V can, for instance, just sample something from private randomness and append this to all its messages. And maybe it can send the same message to all its neighbors. It can do something maybe a little bit like I will just send the next neighbor to each of its edges and so on. So it can do whatever it wants. Okay. And this is the setup we have when we're focusing on this vertex V. I am going to call this IR minus 1 of V to be the inner part of vertex V. Another simplifying assumption I'm making is they're just two neighbors. There's just U1 and U2, which are just two neighbors of V from IR minus 1. And W1 to WK are going to be the fake neighbors that I have imagined. So at this point, U1 is an agent, U2 is an agent, and V is an agent. And all of these vertices from W1 to WK are faked. And V has public randomness resource and this private randomness resource. We want to try and sample all of the messages that V sends, which is M1, M2 till MK for the fake neighbors, and MK plus 1 and MK plus 2 for the real neighbors together from the joint distribution of these messages in PyR. Okay. But what is V using to send these messages? V is going to look at its entire input and maybe something from its private randomness and then it'll figure out what these messages are. But now my claim is you won't be able to do this exactly. And you won't even, like, once you get this input, you're not going to be able to sample this message after. Um, so let's look at U1 and V specifically. Okay. So if U1 is a real vertex, and at the end of whatever sampling process we use, U1 should know what is the message that V sends. Specifically, U1 should know MK plus 1, like it should have the message in hand to continue running this. Let's look at one example. Let's say we just fix a random neighbor that is in um, not U1 and just sends this across as a message. So if V is super, super lucky, V is going to pick U2 as its random neighbor and send it across MK plus 1. But this is just something that cannot happen because at the end of such a lucky message, U1 would know that V and U2 have an edge. But right now, U1 doesn't know. U1 only has a local perspective about its own edges. U1, it is not possible for it to completely know the input of V at all, which means MK plus 1 would depend in a non-trivial way on the entire input of V. So you can't really sample this, whatever you do, to make U1 know this particular edge. So does that answer your question? Okay.
Yeah.
So it's just that we have only very local information and U1 cannot know everything about V. So it is not possible for them to actually sample this MK plus 1 message in a joint manner, which is completely accurate. Okay. So what are we actually going to do? We're not going to sample the input and messages separately. We'll figure out a way to sample them together. So in a very staggered manner, some messages are going to be sampled, then some part of the input, then some messages, then some input, and so on. But together, we would somehow get the right distribution. Okay. Uh, I'm going to go into some ways and resources that we can actually make progress on this goal of sampling messages and inputs together. So the first part, let's just look at this one message M1. So W1 is a fake neighbor at this point. Okay, so let's say W1, this part of the input is fixed. So W1 is a fixed neighbor, and we have said that this is my neighbor. I want to say that such a message M1 is something you can actually sample with this public randomness resource. Okay. And whatever distribution you use to sample M1 is not going to be too far from the right distribution we should have used either. So mainly because from the perspective of V, when it sends this message M1, it is going to look at all its neighbors and send M1 as a message. But when we're sampling this, we won't be able to include this inner part of V, specifically U1 and U2, because this is not something that publicly everyone knows. So you can't use public randomness to do this. But K is going to be much, much larger than 2. So whatever information M1 sends is going to be about a lot of these fake neighbors. So it's all right. Even if you ignore these U1, U2, you'll be okay. Okay, so you're not going to be too far. And this is something you can repeat for, let's say, the next message you want to sample, which is M2 also. And M2's distribution, I can do one thing in addition. I can actually look at what M1 was and then sample based on that. So I can condition on the value of M1 and then sample M2. Without, again, I won't be able to include U1 and U2 because this is not public information. But one thing I will get here is joint distribution of M1 and M2 both together is going to be close to what it should be. Okay, because I've looked at this and then sampled M2. Let's try and repeat this for MK plus 1. And this is where, again, you'll run into a serious problem because we went through this, we talked about this a little bit. Now, MK plus 1 as a message, it exists only if the edge between V and U1 exists. But the existence of this edge at this point is known only to V and U1. No one else even knows this. So no one else even knows that you're supposed to sample such a message. So if you try and sample MK plus 1 using public randomness, you're going to fail because publicly, it's not even information that you know you should sample. And to get around this, this is where we augment the model a little bit more. We have to give a way for V and U1 to sample this message that only they should know, conditioned on whether their edge exists. So we're giving them some other extra randomness resource called pair randomness. This is something that only V and U1 can see. And so with this pair randomness resource, they can sample MK plus 1 based on the edge existence. We're only adding power to the model, so whatever low bound you prove here is going to be true in the standard model as well. Now, I will be ignoring existence of U2 edge because it's not something that U1 knows. But for similar reasons we talked about, K is going to be super large, so U2 edge is something that you can remove. Okay. So when you're trying to sample these first round messages of pi r, we've given them two extra resources. We've given them public randomness and this pair randomness to sample specific messages between inner vertices. Let's see if we can progress to the other real message that we should sample. So U2 is still a real vertex, V is a real vertex, and they should know some message MK plus 2. We'll try the same thing. We'll give them this pair randomness and see if you can make progress. You can. So marginally, for the same reasons, even if you ignore this edge to U1, you would be close to what you will get because K is going to be large. Information about U1 is not going to be transferred. But you will run into another issue. So we threw some example protocols around. Okay, so it is very much possible that these two messages are correlated with each other. You're not looking at M1 and then sampling MK plus 2 based on this. So whatever commonality exists between these two messages, you're missing out, and your distribution is going to be super far. And you're sampling these messages separately. I'm not going to tell you explicitly how this is fixed, but this was one of the big issues we had to overcome. Intuitively, the reason you can fix this is from V's perspective, it doesn't know which are the special inner messages. It can't go and say, okay, so this is the orange one, so I'll say something only to them. No. Whatever it sends across these messages, it has to make it common among all its neighbors. So I'm trying to say it is not possible that MK plus 1 and MK plus 2 have some special correlation that is not present in the other messages. So if MK plus 1 and MK plus 2 have some special correlation, they should have this correlation with the majority of messages that we send also. So this is the reason why you can actually, you have some hope to solve this. Now, I'm not going to go into specifics of the process. I'll just briefly say the overall view. So the first step is going to use this public randomness to sample some of these fake neighbors and messages to them. So this messages when you're sampling to them is going to help you break correlation between other messages you have to sample with pair randomness. So the next step is you look at everything you've sampled publicly, and then you have to sample these messages to U2 and U1. So you use this extra resource of pair randomness you gave and sample these messages. And finally, V knows everything, all the messages that it sends, it has sampled so far. So it's going to look at everything and fill up the rest of its input and all the remaining fake messages that it has to sample by itself. That's it. It's not going to use any other resource. It's going to use this private randomness. So this is all I'm going to say about the sampling process. I will go back to this slide we had at the beginning where we threw around some things that the protocol could do. Okay. So I'll briefly say how we get around, like the main issue here and how we get around this. So we said it could sample a random bit from private randomness and append it to its messages, or even send the same message to everyone. The underlying issue in both of these protocols is just message-message correlation. And in one word, in one phrase, if I had to say how we get around this, we just use public randomness to break this correlation between messages. Okay, so some part of it is fixed, and then you sample the rest based on that. So the next thing we said is going to just send the next neighbor lexicographically or something like this. And why this is not going to be useful to the protocol or how we get around this is that there are going to be a lot of these fake neighbors. So the real vertices will not receive information about each other. They won't be close to each other. So your K is going to be super large. So that's all you end up sending to the inner vertices. So so this is also something we can handle just by increasing the degree of the vertex by a lot. And this will this is the end of the sampling process. After this, let's actually see why we're getting log n specifically and see what we can do. And this is almost the end. I'm going to conclude soon. Okay. So in terms of parameters, we started out with this one round lower bound. This we're going to say we're going to be able to prove that you need omega of n1 communication based on the number of vertices. And the number of vertices is blowing up by a polynomial factor. But the communication required is still going to be exactly the same as the one round lower bound. So omega of n1 is true. You still need that much. And this is going to be n2 to the 1 over c, if c is whatever constant you're blowing up by. And if you continue this all the way till r, nr is going to be the total number of vertices for the r round instance. This will have n1 to the c to the r kind of relationship to n1, and the lower bound is still going to be n1, which is nr to the 1 over c to the r. So if r is super small and it's little o of log n, this term of nr to the 1 over c to the r is going to be little omega of log n. And this will be beyond the budget we have for CONGEST algorithms. So this is why r should be at least log n. And this is why we get the specific log n lower bound also. Now, just to finish the talk, the main result was we proved that round complexity of this triangle detection problem in this CONGEST model is omega of log n rounds. And the main technique was this round elimination framework of Milterson et al. And we adapted it to the CONGEST model with all these point-to-point communication aspects. There are some open questions left. The main question is, can you improve this lower bound to something stronger? And we think that log n should be the right thing that you can achieve realistically. We said very strong lower bounds n to the omega of 1 is going to give you circuit lower bounds. So I'll say like maybe, a couple of sentences about this now. So what they prove is if you prove, and what the Eden et al. Paper gives, is if you prove an n to the omega of 1 lower bound for this problem, you're going to give an explicit function where circuits with log depth need superlinear size. But this is a long-standing problem that we have not been able to make progress on. The current lower bound we can prove on this circuit size is just 3.1 n. So with a slight optimization of their parameters, you can say that even an n to the omega of 1 over log n lower bound will still give you strong circuit lower bounds. But mainly, if you prove some very large polynomial log to the 100 or something like that, this could imply circuit lower bounds as well if current reductions, the CONGEST algorithms get better. So it could imply circuit lower bounds, and there's nothing stopping them from implying circuit lower bounds. So which means log n is the realistic target, we think. And the next immediate question is for other cliques, there are still gaps between the upper and lower bounds. Specifically for cliques of size at least 5, we know that you can do it in n to the 1 minus 2 over p for p-sized cliques, and the lower bound is omega of square root n. And we also know that the gap between these bounds cannot be closed with the communication complexity techniques we talked about. So can you use some of our techniques to close this gap or not? Okay, and that's it. Thank you.
Right. Thank you, Janani. We can either take a few questions now, and then move on to the unrecorded session, or we can maybe open it up.
I had a question.
Yes.
So I was wondering, like, if you had some intuition. So you mentioned that for the listing triangles, we actually have
Mm-hmm.
like an n to the one third lower bound, and guess I was wondering, like, why in your mind, like, why do you think it's so much harder to prove lower bounds for the um triangle detection versus the listing? Like, uh,
Yes. Okay. So when you're listing, let's just look at like a graph with a lot of triangles. Okay, let's say. So even bit-wise, the amount of bits that it has to output is going to be super large. And how that lower bound will go is just so it'll say that there'll be at least one vertex which has to output n to the 4 over 3 bits to output a lot of these, like all of the triangles inside the graph, which means if you restrict the total communication to just n log n in one round that it receives from all its neighbors, you'll get n to the one third. So here the output is one bit, even though it can depend on the graph very globally. There, the output, even the bit complexity is just super large, and you can use that to get very strong lower bounds.
I see. Thank you.
Yeah, okay. That was a good question. Thank you.